So we'll continue with my second lecture. And so what's nice with the slides is that I can come back to what I discussed yesterday. So I will just recap just a few things that you will need for my 2-day lecture. So I give some setup about games and what are the motivation behind that. But at some stage, I just want to recall you that if I play Wythoff games, did you try the exercise I let you to do yesterday? You have this. So maybe you try or not, but I will write it down on the blackboard because I will use it later on. If you play Wythoff game, whatever are the rules of that combinatorial game, then the set of P position, and P position means just the losing position, is the set of integer part of n times phi, where phi is the golden ratio, and n times phi square. And also, the question was asked yesterday, you have the symmetrized version because otherwise one pile is bigger or the other one, so you can also have all those P positions in the reverse order. So this is something I will use. Then my main motivation was something like the following one. I give you a bidimensional array like that one. And so here you can see this as a bidimensional sequence. So I will call it G of n, which is for another game, which is the game of Nim. And so G of n, you can see it as a map from n2 to n. And my main question was, what is the structure of this bidimensional sequence, right? So what can be said about the structure of G of n? Even if we know how to compute it thanks to a Nim-sum, but I would like some more information about that. So this is why I introduced in the second part of my talk yesterday, I introduced things like k-automatic sequences and then k-regular sequences. And so this was the slide I used yesterday, and it was case of one-dimensional sequence, like infinite word. And today I will move to a multidimensional framework. This is why I put this nice shirt to have a bidimensional tiling, a discrete shirt, whatever you want. So, okay, and so I will also need this kind of construction. So just to recap, just this slide, this was an example of a three-automatic sequence. But what you need to have in mind is just that on the left side you have a morphism, and you will iterate this morphism to produce some infinite word. And on the right side, this is exactly the same game, so to speak, but here you will use some finite automaton to produce any element of the sequence. And you fed this automaton with base 3 expansion. And when I give you the morphism, you can build the states of the automaton and the transition, right? Remember that? Just remember you, if I have an A here, it comes from this letter A, and if you look at the image, which are A, B, and then C in that order, it gives you the three transition with 0, 1, and 2, okay? And so, I introduced yesterday, so k-automatic sequences. So if you have a sequence over a finite alphabet, and so this was a case of k-automatic sequences. But then if you think about my table with integer inside the table, then I have to move from a finite alphabet, so the alphabet R is a finite alphabet. I have to move also to sequences which take unbounded value. And this is why I introduce also the concept of k-regular sequences. And how do you move from one kind of sequence to the other one? When you introduce the notion of kernel. And so I will also need this at some stage. So where is the kernel? It's over here. So the k-kernel of a sequence, so the base k is fixed, right? And it's just a set of subsequences. And this is a set of all the subsequences that you will get by taking every single element out of k and you shift it and you repeat this operation, okay? So in this case, when you have a k-automatic sequence, the k-kernel is finite. So if you look about the k-kernel here, it is finite. And when you move to k-regular sequence, then the k-kernel will be not finite, but finitely generated. So these are the two main differences, okay? So this is my 1.5 hour lecture made in 5 minutes. Okay. So, where was I? I was more or less here. Okay, I stopped there yesterday. And maybe before moving more to the following part of my talk, I had a few backup slides yesterday, maybe to motivate the study of, let's say, automatic sequences or morphic sequences, so sequence obtained by substitution. So just to make a, let's say, a short break, when I give lecture to my student and I want to introduce them to combinatorics on words, and why is it fun to play with words, this is one of the motivations that you can consider. So just 3 slides to give you why you can study infinite word, morphic infinite word, and what it is useful in combinatorial words. So maybe you all know that, but I will give you the most simple theorem you can imagine about words. This is how I advertise my lecture for my future student. Please come with me and study with me. This is so easy. So the most easiest theorem is the following one. I have a 2-letter alphabet, right? So AB is my alphabet. And first I have to tell you what is a square. A square is just the same factor repeated twice. Okay, like in French the word bonbon is a square. And so over a 2-letter alphabet, you cannot avoid square. The proof is very easy. Try to build a word without any square in it. I start with an A or B. It doesn't matter, right? So if you start with an A, that's the first letter of my word. If I don't want a square, then the second letter will be not an A, it should be a B, right? And I try to build the longest possible word without a square. So may I write a B? No, because then I will have BB, which is a square. So I have to write an A. And we are done. Because now, either you write an A, and so the word will contain AA, which is a square, or you write a B, and the whole word is a square, AB, AB, right? So, very nice theorem. Over a 2-letter alphabet, this is the longest possible word that do not contain square. And so what kind of question may you ask with that respect? Either you can increase the size of the alphabet, can you build a long word, or even better, an infinite word over a 3-letter alphabet without square? Or if you stuck with a 2-letter alphabet, can you avoid something more difficult than just square? Can you avoid cube? And something which is between squares and cubes is an overlap. So what is an overlap? So to say it's just a bit more than a square. It's a square, and then you just add the first letter of the word you had before. So yesterday I was thinking about some real word that contain an overlap, and I found a small village in the Netherlands, which is lek, keur, keur, keur. And so just to confuse you a bit more, because yesterday I discussed the kernel of a graph, then the k-kernel of a sequence, and now you have the village which is le keur kerk. So this is another kind of kerk, okay? Which just means, I guess, more or less in Dutch, kerk is a church, and lek is a river in the Netherlands, so probably it's a church near this lek river. And so in that word, you see some overlap. You have ker, and an extra k, right? So this is an overlap. And then you can prove that the two-morphs word, you recognize this word. Actually, there exists only two infinite words, Fibonacci word or the Tumors word, right? This is the only two words you only see. No, that's not true. You have also Arnaud-Rosy word. No, you have three kinds of words. And so the Fibonacci word, you can prove it. You can prove that this is an infinite word that will avoid this kind of overlap. Okay? So there is no overlap in the Fibonacci word. I say Fibonacci? This is Tumors, right, right. Yes. So the Tumors word has no overlap. And you can do the proof in a combinatorial way, like you can find a proof of this result in the classical Lothair's book, for instance. And so you see, if you move from square to overlap, you can avoid them with Tumors. And then the other question, if you would like to have more letters in your alphabet, then can you avoid square? And the answer is yes. And you can almost do it using Tumors. Because in the Tumors word, you never have, of course, 3 consecutive A, nor 3 consecutive B. And so you can cut in a unique way. You have some kind of code. You can cut Tumors word into factors of the kind A, B, B, A, B, and just A, just like I did it there. And then I recode those blocks depending on their lengths, 3, 2, or 1. And so the word over there is a word over a 3-letter alphabet that avoid squares. Why? Because if you have a square somewhere, imagine you see somewhere a square that will occur, then you have the first next symbol there, but all these 3, 1, 2, 3, correspond to words starting with the A. So this means that if you add some square in this word, you should have an overlap in the Tumors word. And we know that that is not the case. So this is one of the reasons why I like to iterate morphism to produce infinite word. You get a lot of information that you may use to solve questions like that one. And if you do something a bit more complicated, if you have a morphism of constant length, 85, and if you iterate this morphism, then what you get is a word that would avoid abelian square. So what is an abelian square? This is more or less just a copy of 2 times the same factor, but here you can permute letters from one of the 2 factors, right? So you have 2 factors with the same abelian vector. And so here again, you can prove that if you iterate this morphism, you will get some infinite word avoiding that kind of repetition. And since Julien was here, I have also an extra slide with a variant of this kind of question. If you think about abelian repetition over a 2-letter alphabet, if you just have 0s and 1, meaning that 2 factors of the same length are abelian equivalent, just mean that the sum are the same. So if you move to a larger alphabet, you would like to avoid, let's say, here, this is an abelian cube, because you have 3 times a factor of length 2, but it's not abelian in the usual sense. It's abelian in the sense of the additivity. I mean, if you sum up 0 plus 4, it's the same as 1 plus 3, and it's the same as 4 plus 0. And so if you iterate that kind of morphism, then what you get is an infinite word that avoid repetition of 3 consecutive factors of the same length and the same sum. So you can play with morphism and answer a question like those one. So this was just some advertisement to do some combinatorics on words. So now let's back to the topics of today. And so this slide is more or less a copy of what I did yesterday, but now I move from the framework in 1 dimension. I just don't have words, but I would like to produce pictures. So let's say bidimensional infinite words. And so what you could do, remember, a k-automatic sequence is just obtained by iterating a morphism whose images have all lengths k. And so now what I could do is say, okay, each letter will be mapped onto a square of size k. And to be able to iterate the process, for instance, if I iterate starting from the letter A, then what I should do is say, let's say in the lower left corner, I have the same letter that will occur again. And so instead of having longer and longer prefix, I will have longer and longer square that will converge to some infinite word. So just like in York lecture or in Natalie lecture, I will still use the usual, let's say, big ball topology. If we have something close to the origin, which have correspondence on a large block close to the origin, then the two sequences are converging. The sequence is converging to some infinite sequence, to some infinite bidimensional picture. And if you remember that I can move from uniform morphism to automaton, you can do the same. But instead of having transition just labeled by one letter, I have transition labeled by pairs of letters if I want to produce bidimensional picture. But then you could think that you could have some problem because, I don't know, if you want to feed an automaton and you will read things like this, what you are feeding the automaton with, you should have two words of the same length. So usually, if you want, I don't know, what is going on in position 3, let's say 3, 9, and if you work with base 2 expansion, then 3 is written like 1, 1, 9 is written 1, 0, 0, 1, and then you have two words that do not have the same length. And so what you do to be able to enter those words into your automaton, then you just have to put extra zeros here. And so these two words, you cut them like this, and you will enter the automaton by reading digit by pairs of digit by pairs of digit, and then you can do the job. And so the idea is that it's exactly the same proof. Either you consider this kind of morphism, or you have some automaton that you will feed with, let's say, pairs of words of the same length to produce the entry that you like. So this is exactly similar to what I explained yesterday. And also what you can do, but I won't discuss it today, you still have this logic formalism that you may use if you like. And so still you can define formula in first order logic to say, okay, I have this kind of symbol in that or that position. So you can also play the game with this multidimensional setting. And also, what I will discuss is that you also can define a kernel and the same characterizations still hold, so you can define a multidimensional kernel. Okay, so here is an example. My morphism or substitution, if you want, is this one. So let's say the blue square is becoming this 2 by 2 picture, this pink one is becoming this one, and I start from the lower left corner, and what I get when I iterate is a picture that is growing like this. So this is a bidimensional 2 automatic sequence, okay? Just like yesterday, if you want to know, okay, this one, so this is part of a, let's say, 2 automatic bidimensional sequence, and you would like to know this particular cell, where does it come from when you iterate the morphism? So this one is in position 12, 10, and I start with 0. And so 12, 10 in base 2 is written like this, 1, 1, 0, 0, 1, 0, 1, 0. And more or less, you just have to divide by 2. So I just have to remove the last digit. So this means that this 2 by 2 block comes from this blue cell, which is in position 6, 5. And again, now this blue cell in position 6, 5 comes from some cell before it. So I just divide by 2 and I forget about the last digit. And so it comes from 3, 2. So this means that the blue cell here, its image is the 2 by 2 cell which is here. And again, this blue one comes from the block 1, 1 here. And so you can keep track of the past to exactly know each element somewhere in your grid, where does it come from when you iterate the morphism again and again? And this is more or less just Euclidean division by the base you are considering. Just like yesterday in one dimension, you do exactly the same in 2 dimensions. And you remember that to be able to define k regular sequences, I need a finiteness of the kernel. And so what will be the kernel in 2 dimension or in d dimension? That's actually the same. You will just consider some particular subsequences of the whole sequence. And so k is fixed, as usual. You look at the subsequence of this kind. So you multiply the 2 components by k to the I for any non-negative I. And you fix some remainder R and S for the 2 components. And so another way to say that is that you will consider all the indices that will have some specified suffix written in base k. So this means here that if I'm interested in the remainder R and the remainder S after multiplying by k to the I, this just means that the 2 expansions that I will look should end with 2 suffixes of length I with an end of the kind, the representation in base k of R and the representation in base k of S. And so this just means the following. The k-kernel will contain all the subsequents like those one. For instance, you take all the even entries for one of the coordinate and the even entries for the other coordinate. This is why I write 0, 0, which means even, even. Or I'll consider the odd, even, odd, the even, odd, the even, even, and so on. If I've considered all possibilities after multiplying by 2, now I look multiplication by 4, and so I will have, for instance, this one, and so on and so on. So you possibly have infinitely many subsequences, but then k automaticity will be exactly translate into the terms of the finiteness of the kernel. So all what I explained yesterday still work in this multidimensional setting. And so let's come back now to the game of Nim. You remember that I have this bidimensional sequence, and if you remember, if I give you x and y, then it's just the Nim-sum of x and y. And what is a Nim-sum? You write x and y in base 2, and you do addition column by column without carry. So you just count if you have an even or odd number of 1 in each of the column when you do addition. And so now I can prove that this bidimensional array is 2 regular. And so what is the meaning of 2 regular? You have this array. You look at all the subsequences in the k-kernel, and being 2 regular must mean that you have a finite number of sequences such that every element in the kernel is a linear combination of this finite number of sequences. Okay? And so here is the proof. The proof is pretty easy. What can I say about the value, the Grundy value of 2m, 2n? You will say, okay, I know that this is just a Nim-sum of 2m and 2n, right? But, so you write m, this is a number written in base 2, you write n, you do the Nim-sum of these 2 numbers, right? But here I ask you, what is the Nim-sum of 2m and 2n? So you just have to add a 0 on the right. This is multiplication by 2 in base 2. And so what you get is that you will end up with exactly 2 times what you had before. Do you agree with me? Here I have this multiplication, and so this gives me m plus n, but I have this 0 digit here, so it's just twice what I had before. You get that one? Right? And so the other has the same game to play. Because if I look at what is the value for 2m plus 1 and 2n, then it's just this over here. And what I will change here is what? I just put a 1 here on the right of m. And so this means 1 plus 0 will be a 1. And so what I get is twice what I had before, because I have shifted everything by 1, and I add a 1. So this is why I get this formula over here. In a symmetric way, this is the same formula here. And for the last case, if I have 2m plus 1 and 2n plus 1, then I add a 1 for both of them. But if you do that, remember that for the Nim-sum, 1 plus 1 is 0. So what you get is twice the Nim-sum of m and n. So this is exactly what you have here. And now I have to convince you that these four relations are enough to prove what I want. With only these four relations, any element of the kernel will be a linear combination with coefficient in z of the sequence g m of n and the constant sequence, which is always 1 wherever I want. I will convince you just on an example. So you don't believe me. So I consider this element of the kernel, right? This is a subsequence of the full sequence. 8m plus 5 and 8n plus 2. And so how do I proceed? Okay, 8m plus something, so I first do this. I write this as twice something plus 1, because I have a 5 here. And here it's 2 times 4n plus 1. So I replace these two 1 by these two guys. But here I can apply the relation I just saw on the previous slide, right? It's 2 times something plus 1 and 2 times something. So what I get is 2g of what was inside plus 1. But then you iterate. You may apply again the same relation as before. I replace this 4m by 2 times 2m, so I get 2 times 2m plus 1, and I do the same trick here. So I can apply the same relation again, and I can apply the same relation again. And so at the end, you see that exactly this sequence, or any element of the sequence, is a combination of g of mn and 7 times 1, which is the constant sequence. So are you convinced that any element of the two kernel of the original sequence can be obtained this way? All you have to do to prove that kind of result is that at some stage, here I was lucky because it was just 2 times the initial value, but maybe you have to look for some larger power of 2. But if at some stage for a given power of 2 and all the possible remainder, you will express everything in terms of something which smaller power of 2, then you are done. You can iterate the process and you find a finite number of sequences to express any sequences in the kernel, right? And so we know this. So we have this extra information about g of n. So we know that it is 2 regular and it is generated just by 2 sequences. And so I can also use this relation that I get here. You see, if you know the value of g at position mn, then you can compute position at position 2m, 2n plus 1 or not. So what does I mean by that? I mean the following. I can produce all my table just with these two relations, because if you know what's going on here, I know exactly what will going on in this 2 by 2 square, right? Because if it's the position mn, then here you have the position 2m, 2n, 2m plus 1, 2n plus 1, and so on. And so 3 times 2 is 6, plus 1 I get those two 7, and I can continue this way. For instance, why do I get 12, 13, 13, 12? It comes from this 6. So this 6 will produce this block, this 7 will produce that block, and so on. This 0, for instance, will produce this block 0, 1, 1, 0, and so on and so forth. So now I know exactly the structure of the table just by knowing that the sequence is too regular. So I'm happy with that. I know many things. Okay. So next, let's look at this table. What is this table? This is just exactly the Grundy value, but now not for the Nim game, but for the Wythoff game. So remember, for Wythoff's game, what do? You have two piles of token. Just like Nim game, you can remove whatever you want from one of the two piles, but you have an extra rule. You can also remove things from both piles, but you have to remove the same number of tokens on the two piles simultaneously. And so, how can you compute this table? So, not as before, this is not the same formula anymore, but remember that to know what is the Grundy value somewhere, you just have to know what are the Grundy value of all the options. And so, in this point, why do I have a 1? What is available to this position? You can play in one direction, you remove something on one pile. You can play in the other direction, you can remove something on the other pile, or you can play on both piles simultaneously, so you play to a parallel on the diagonal. And what you have to compute is the max, the minimal exclude value, so the only value that you don't see before. So why is it a 1 here? It cannot be 0, because I see a 0 here. But if you look, there is no 1. There is a 2, okay, there is maybe some 3 over here, but there is no 1, this is why I have a 1 here. So if you want to compute this table for yourself, it's not difficult. You just have to compute it line by line like this, with a constant x plus y, because when you have computed all this part, all this region of n squared, you know everything you need to compute the value that will occur later on. So you can compute this table. And the question is the same. Could I say something about the structure of this? But it turns out that it's a very difficult question, actually. The table seems very simple. For the game of Nim, everything is very easy. I have just 4 relations and it's pretty simple. But here it's not so easy. There are many people who work in that direction. So, for instance, in the 90s, Frankel and Blas considered Sprague-Grundy value for Wythoff game, and they were only able to prove some few results. I mean, it's not even so clear where occurred the 1 in this table. And then people look at some kind of generalization of this table, and so really not so much is known about that. So I just quote a part of the book I showed you yesterday, one of the 3 main references, let's say, in combinatorial game theory, the book about Siegel. And so he said the following: no general formula is known for computing arbitrary g-value of Wythoff game. In general, they appear to be chaotic, though they exhibit a striking fractal-like pattern. And so it seems very hard to say a lot of things about this quite simple table. So it's quite challenging. And so here, maybe it's not so nice because maybe the PDF file, it was you see, you have some too big ratio of compression, but it's the first value appear like this. So more or less, you have these 2 lines here where you can maybe more or less recognize where the P position of the game were. And so when you get bluer, you get higher G value, and green, light green is closer to value close to 1. And so this is how the value looks like, but it's too much compression, you see. You lose something here, but you can compute it pretty easily. I just write down some very small Mathematica program, but if you prefer Sage, that's the same. I mean, it's just a 3-line program to just compute those values recursively. So it's not a big deal to do that. And so, just to tell you a few of the things that are known about this table. So, for instance, Blas and Frankel show the following. If you follow something which is a parallel to a diagonal, then you will see every single possible integer at least once on this diagonal. Actually, exactly once, because you have the max, so you cannot not have twice the same value occurring on such a parallel. And in some sense, they prove that all the 1 that occur in the table are in some sense close to the 0. I don't want to tell you what I mean by close, but you see here that the 1 are really next to the 0 here, that's the same for here. And also, they devise some kind of complicated algorithm to find where all these 1 positions are. You could say, okay, I can just have to compute the table and that's it. But their algorithm is a bit better in terms of complexity. But it's quite intricate just to get the 1 in that table. Also, something nice that appeared, they have some kind of periodicity that occur on every row and line. Of course, because it's symmetric, so you will see the same things horizontally and vertically. And so the kind of periodicity that you can see is the following. It's what they call additively periodic. What does it mean for a sequence to be additively periodic? Just mean that if you look at what's going on for index j plus p, it's what you add in aj, but you have to add p. And so just to convince you, I draw it with, I take the, let's say, row or line number 5, and when I look at something of the kind n plus 24, what you get back was exactly what you add in position n plus 24. And so this graph is just the Grundy value where the first component is fixed to 5, and I subtract n. So instead of having something which grows linearly, I get back to something which is periodic, which is the meaning of being additively periodic. So you have all this strange kind of behavior. And now, instead of tumors, this is really Fibonacci that will enter the picture. So at this point, I would like to convince you what is the meaning that the Fibonacci word is coding the p position of the Wythoff game. So you just have to remember the exercise of yesterday. So I will make use of this. We know that, okay? This is something we know. We know that the p positions are given by this integer part. There is again another way to discuss or to define or introduce Sturmian words. In York's talk, Sturmian words were introduced in terms of factor complexity, in terms of coding of rotation, but you can also obtain them, let's say, in a mechanical way, just like looking at differences of integer part of multiple of an irrational number. That's another equivalent way to define a Sturmian sequence. And so first, I start with Betti theorem. So what does it say? If you take two irrational numbers, and if you have a condition like this one, 1 over alpha plus 1 over beta is equal to 1, then with that condition, if you look at the integer part, the set of integer part of n alpha and beta, let's say with n equal at least to 1, then you have a partition of the positive integer. And so in particular, if you are considering the golden ratio, for the golden ratio, you know that it's a root of x squared minus x minus 1, which is equal to 0. Then this means that phi squared is equal to phi plus 1. And if I divide both sides by phi squared, I just get what? 1 is equal to 1 over phi plus 1 over phi squared, right? And so actually, I can make use of Betti theorem. I have exactly this condition. So what does it mean? This means that if you look at the integer part, the sequence of integer part of the multiple of the golden ratio, and the sequence of integer part of the multiple of the square of the golden ratio, then you have a partition of the positive integer. So take the positive integer. I have written in red the integer part of multiple of phi, and in black the multiple of phi square. So I get this sequence. And what is the link with Wythoff game? I would like to know what are the p position. So I just have to know what is the first red element and the first black element. So 1, 2 is the first losing position. Then I look at the second red element and the second black element. So 3, 5 is the second p position, and so on. Yesterday, when I play with Shigeki, and I was a mean player, I give him to start with the position 4, 7. And so you see, 4 is the third red element, and 7 is the third black element. And so with this sequence, this is exactly the result of yesterday. But from this, I get back also the Sturmian word. Why? Because if you look at the difference 2, 1, 2, 2, 1, 2, 1, you produce this word. And actually, it's exactly the same as Jörg, but if you switch 1 and 2, I guess. And also, this is exactly the Fibonacci word. So another way to view this word is to say, okay, you take some straight line with irrational slope, and you look at the closest broken line which remain with integer point on the lattice, but just below that line. And this coding, which is equivalent to what Jörg said yesterday or even today, means that you have a coding, get back to this word. So now I guess you understand my meaning, why the Fibonacci word is involved when you play Wythoff game. Because if you know Fibonacci word, then you know what are the p position. That's the point. If you forget about everything I told you here, and if you just want to play Wythoff game, what you should do, if you know Fibonacci, you know that A gives AB and B gives A. Then you compute in your mind, in your head, A gives AB. And you know that Cobham called morphic or substitutive sequence, he called those sequence stack sequence. You know why? Because I have one hand which is the reading head, and my other hand is the writing head. And so when I read A, I write AB. Now I read B, I write A. I read A, I write AB. I read A, I write AB. I read B, I write A. And I continue this way. And so I tag the letter I've seen before. And so this is why the original Cobham's paper on automatic sequences are called tag sequences, because you look and you tag the letter that you have already read when you are producing this word. And so my message is the following. You build in your head the Fibonacci word. You write down 1, 2, 3, 4, 5, 6, 7, and so on. And so here you have a coding of the p position. You just have to look at where is the nth letter A and the nth letter B. Okay? So that is equivalent to that. I write it here. I looked at the nth A and nth B. It's important for me later on. Okay. What did I do yesterday? Yesterday, I had morphism of constant length, remember? And from morphism of constant length, I was looking at automata, which were corresponding to the morphism. And I was feeding this automaton with base k expansion. Why base k? Because morphism of constant length k. So here, my question is, Where was the remote control? That's my first question. But the main question is, can I do the same? Ah, it's here. So I have a morphism, no, the Fibonacci morphism, or Fibonacci substitution, which is no more of constant length. One image is of length 2, and the other one is of length a. So can I do the same as yesterday? So instead of having a uniform morphism, and so instead of having base k expansion, can I do the same trick? And the answer is yes. So first, I guess it's clear that you get this automaton, right? Why? Because the automaton is exactly what the morphism told you, right? You know that the image of A is AB, and the image of B is A. This is exactly what is encoded in this automaton. The image of A starts with an A, because I have a loop with 0, followed by a B. And B has just an image of length 1, so I just have an edge, labeled 0, going there. So let's say this is the easy part. But now the question is, if I want to produce the nth letter, I would like to know, do I have an A or a B? What should I enter in this automaton? And the answer is the following. You just have to look at all the words that are accepted by this automaton. So what I mean, I just look at all the possible paths, starting from the initial state, and my initial state is A. Why A? Because I iterate the morphism starting with A. So this is why this is my initial state. And I look at all the words that I can be seen through the automaton. But I discard those starting with 0. Okay? Just for some technical reason. And so I have ordered this word first by length and then by lexical order. Okay? And so if you consider these words and you plug them into this automaton, the state you will reach will give you exactly A or B. You get it? So if you want the first one, it's A. How do I get A? I just read nothing, epsilon. So it's A. Then I should have a B. If I read 1 from A, I go to B. Then I should have a A. If I read 1, 0, I have a A. Then again a A. If I read 1, 0, 0, I have a A. So feeding the automaton with this sequence gives you exactly what you want. But do you recognize this sequence of words? It's not, of course, it should be related in some way to Fibonacci and things like that. And I don't know if you recognize it, but it's exactly the Fibonacci or Zeckendorf numeration system. So what do I mean? You know the Fibonacci sequence? I start with 1 and 2. So 1, 2, 3, 5, 8, 13, and so on. And if you want to write down some integer, you just have to decompose it using Fibonacci sequence. And you do it in a greedy way. This means that you always try to eat the largest possible entry of the sequence. So I don't know, if you want to write 11, 11 will be written how? It's 8 plus 3. So this is the Fibonacci expansion of 11 written using this Fibonacci system, which is sometimes also called the Zeckendorf numeration system. And I like to mention that because Zeckendorf was a Belgian military physician working in the Belgian army, and he was living in Brussels, and my PhD advisor at some stage visit him and help him write his paper because it was not a professional mathematician, and so he didn't know how to write math and so on, and so that's kind of a funny stuff. And also he published his result in the Bulletin de la Société Royale des Sciences de Liège, so from the local bulletin from my own university. So in somehow I'm linked to Zeckendorf, so that's a nice story. So what the summary of what I did here? So if you want to know the digits occurring here, you just do as before for automatic sequences. But now you have to change the numeration system. You write down number using the Fibonacci sequence. But maybe there is something, a bit technical. You see, to get exactly A, B, and so on, I start with 0, 1, 2, 3. So this means that I'm feeding the automaton there with the representation of 0, 1, 2, 3, 4. That's not a problem, but when I'm playing Wythoff game, I have to start with 1. So I have this small shift of 1 unit, which is a bit not so nice for me, but I have to deal with that. And so what I just told you with Fibonacci is quite general. So the result there is quite ugly, but it's not difficult to explain. What is on this slide is just the following. What I say is you just have to do what I explained with Fibonacci with any substitution you like. So if you give me a substitution, constant length or non-constant length, whatever, so I don't know, let's say A gives ABC, B gives non-constants. So let's say B gives CC and C gives A, something like this. What says the theorem is just from this morphism, you just define an automaton. I have 3 states, just like before, A, B, C. The image of A starts with A, then B, then C. The image of B is 2C, so I write 0 and 1. And the image of C is just A, okay, with 0 here. So you have this automaton. And then what you do, you look at the language corresponding to this automaton without words with leading 0. So what are those words? I have the empty word, then I have 1, then I have 2, and so on. I have 1, 0, 1, 1, and you continue this way. And so if you want to know, if you build the sequence by iterating the morphism, okay? A gives A, B, C, B gives C, C, C gives A, and so on. And if you want to know what will be occurring in position n, all what you have to do is to take this sequence of words, look at the word in position n, and plug it into the automaton, and the output will give you exactly the digit you want. So this is exactly the same. And so here you see that the language here is replacing base tree expansion from my first example in the automatic case, or with replacing Fibonacci expansion in the Fibonacci word. So that's the main idea. So there are just notation, but that's really what's going on there before. Okay. So this is why I should speak about, let's say, L like language automatic sequence. You give me some automaton, some language, and I build sequence like that. And so, of course, this language can be linked to some numeration system, and so you have many non-standard numeration systems that are playing there behind that. Okay, so let's come back to Fibonacci and see what's going on. You see here, if you rotate your head by 90 degrees, you have exactly all the words I was discussing before. This is just the Zeckendorf or Fibonacci expansion of the first integer. You agree with me? If you are not familiar with that, it's not difficult. 1 is just 1. 2 is 1, 0. 3, be careful, it's not 1, 1, because you never have 2 consecutive 1. Because if you add 2 consecutive 1, then by greediness, you should have chosen one term larger, right? So 3 is 1, 0, 0, 4 is 1, 0, 1, 5 is 1, 0, 0, 0, and then you continue like this to produce all the integer. So they are written over here. And so Now you can tell me, in the Fibonacci world, how do you know if there is a A or a B? I mean, can you tell me in position n, is it a A or a B? Well, it's a difficult question, maybe. You're feeling hungry, maybe. But from the automaton, you are feeding the automaton with Fibonacci expansion. And if you look at the automaton, when do you end up in an A? You will end up with an A if it ends with a 0. And you will end up in a B exactly if it ends with a 1. So you know precisely here when you will have an A or a B. You just have to write n using Fibonacci expansion. And if it's n with 0 or 1, you know if you have an A or a B. Okay? And it's even more than that. You can also, just like yesterday, keep track of the past. What do I mean by that? I mean, you know, when you build the sequence with your two hands, but it stretched too long at some time, but you try to build your sequence like this. At some stage, this A will produce, I don't know, A gives AB, B gives A gives AB, then this A is producing this AB, right? And then this B will produce a A. And so you would like to know, okay, this A or this B is coming from some letter occurring before, but which one? And this you also know. Exactly like you did, or like I did with base 2 and 2 automatic sequence, I was just dividing by 2 to look where it comes from. And it's the same game here. This AB, corresponding to these two Fibonacci expansion, come from this A. And how do I know that? I just have to discard the last digit. So these two come from, let's say, 100. And this A is actually the image of this B. I discard the last 0, I have 1 or 1, and so this B is producing that one. So if I know the Fibonacci representation, I know the past. I know where it comes from. Yeah, but B's only comes from image of A, right? And what I would like is to know where is the nth occurrence of A and the nth occurrence of B, because I would like to play Wythoff game. And so if I know where is the nth letter A, this nth A will produce the nth B in the sequence, right? And so I guess this is more or less what I have written down there. You see, the nth letter B is coming from the nth letter A. If in some position J I have an A, so this means that the Fibonacci representation of J ends with a 0, and therefore I will have a AB somewhere, and where is this somewhere? It's in position corresponding to L, which is U01 written in the Fibonacci expansion. And similarly, if I have a B somewhere coming from expansion V1, then it will produce later on a A with position corresponding to V10. Okay? So, my only problem is that I have to deal with, I start with 0 with all what I'm seeking here. You see, the first index is 0, but in Wythoff, I start with 1. Okay, that's my only little problem. So, to summarize what I did up to now, do you agree with me that the nth P position of Wythoff game is given by the position starting with 1 of the nth A and the nth B in the Fibonacci word? Remember, 1, 2, 3, 5, 4, 7, and so on. So I start with 1. But what I know about A's and B in Fibonacci word are with index starting with 0. And so if I consider that I have a position with x less than y, just because I can do the symmetry just like usual, I say that I have a p position, xy is a p position, if the representation of, unfortunately not x, but x minus 1 and y minus 1 is of the kind u0 and u01, right? I know that I just add a 1 here because I know that the nth b is coming from the nth a. This is why I have a 1 here. But you will tell me, okay, I give you x and y, not x minus 1 and y minus 1. So can I do plus 1 more or less? And I do hope that we can all do plus 1. In theorem, that should be a pity if no one could add 1, but it's not a so easy question because I have to add 1, not in the usual way, but using Fibonacci expansions. So, instead of having x minus 1, I'm looking at x, and the same for y, and so you will tell me, oh, it's not so difficult. I have a word of that kind, I just want to add 1. So I take the value of this, I add 1, and I look at the representation that I will get. But do you see the problem? If I give you 3, 1, 0, 0, and you want to add 1, easy. 1, 0, 1, do the job. No problem. But if you start with 4, and you want to add 1, then here I have a problem because I have 1 plus 1. Okay, it's 2, but this means that the 2 will move to 1 digit to the next rank. Then I have 2 consecutive 1, and then I have a carry that will propagate. So adding 1, I have to deal with the case, do I have a 2 consecutive 1 or not? So I look at u0 and u01, right? For the x and y coordinate. So let's start with the easy case. If u end with some 0, so u is of the form u prime 0. And since I would like to know what's going on with u0 plus 1, it's easy. I have 2 0 here, so it's just something like this. And for the other one, it's u01. Remember, u is u prime 0, so I have u01. Why do I have u01? Because it's exactly what I'm interested in here. So I have u01 here. And if I add 1, okay, 1 plus 1 is 2, so I move the 1 here. So pretty easy. This is what I get. And so in that case, what do you see? xy is a p position of Wythoff game. If what? Here I have no 0 at the end. And here I have exactly the same expansion shifted by a 0. So I have an extra 0 here. And now I have a more nasty case. So imagine now that u is not ending with 0, but is ending with a 1, right? But I know that u prime ends with 0. Why do I know that? Because it's a valid expansion. It's a greedy expansion. So I do not have 2 consecutive 1. So I do the same, but you will tell me, no, there is a problem, because if I do this, I will have 2 consecutive 1 here or here. But anyway, there is a way to proceed with that. You have a transducer, exactly like in the Emmanuel talk. So you have a transducer that you can use. If I give to the transducer a Fibonacci expansion, it will output the Fibonacci expansion of the next integer. So the successor function can be computed by a transducer, reading entries from right to left. So here is the transducer, and to really see that it moved from right to left, I put the initial state on the right, and so you really have to read things from right to left in that way. And so the meaning of this transducer, just like when Emmanuel wanted to glue together tiles, here is more or less the same idea. You enter some number, and it outputs the Fibonacci expansion of the next integer. And so you see sometime when you start reading a 1 or a 0, then it output nothing at first. Sometimes it could output 2 digits at a time, but at the end, when you reach some final state and you have read all your word, you have produced what you want. And so, what kind of entry do I have to this transducer? You see, I have entry of that kind. U prime 1, 0 or U prime 1, 0, 1. And so I look at U prime 1, 0, I look at U prime 1, 0, 1, and I go through the transducer and see what can happen. And so I start from here, and so what do I have to read? 0, 1, 0, then a block of 1, 0, 0, 1, 0, then a block of 1, 0, sometime here, and then I end with 0, 1, and then x, which could be anything which is valid. And if you look at the output that corresponds to that, you will get this word. And if you do the same with the second component, which is here, you will output that word. And if you compare these two words, what do you get? They are the same, but the second one is shifted by 1, and the first one ends with an even number of 0. And if you don't have a word of that kind, if you just look a bit about what kind of word can be valid expansion, then the only other possibility is that one, and you will output similar things. By similar, I mean the following. The first one shifted by 1 is the second one, and you again have an even number of 0. And these are all the possible cases. So now putting everything together, I know all what I want. I know what are the p positions. I know that they are coded by the Fibonacci word. And I can tell you exactly when you give me x and y, you write them in the Fibonacci numeration system. And I know precisely when it is a p position or not. From this analysis, I know that x must end with an even number of 0, and I and y must be the same shifted by 1. And so this is a result that Frankel obtained in a different way, but it is exactly that. So even if you play with very huge pile of token, you know, if you can write down number like this, you know in linear time, with respect to the length of the Fibonacci expansion, which is logarithmic to the entry, you know if you want to start to play or not. Okay. So remember the general tone of my lecture is about also shape symmetry. And so shape symmetry will now enter the picture. At least I can start this today. What is this table? You say, okay, this is again another table. In one sense, this is a simple table because you just have zeros and 1. So I'm not anymore discussing something which is, let's say, 2 regular or Fibonacci regular or whatever. I would just to stick to something more easier like classical automatic sequence. So first, I just put 1 exactly where you have p position of Wythoff game, right? 1, 2, 3, 5, and so on. 4, 7, like yesterday for Shigeki. So you have all these p position of the Wythoff game. And the question is, I have some bidimensional infinite word over 0, 1. Can I produce this in some way? So the question is, can I produce some morphism to get this infinite picture? And the answer is yes. Here is the morphism. You say, oh, that's a bit strange. And I agree with you, it seems to be quite complicated. And at first, you even can ask me, oh, okay, it looks like a morphism, but it's not so nice as before. When I add just 2 automatic sequence or k automatic sequence, I was just playing with image of letters that were just squares of the same size. And I was just putting together squares of, say, size k, and when I iterate, I get a square of size k square, and so on and so on, and it was pretty easy. Here at first, if you look at that, and you start with A, you are not even sure that you will be able to iterate things, right? Because maybe if you have different rectangles, at some stage you will tell me, okay, but I have rectangles, but how do I put them together? I have no condition to be sure that I will get to something which is nice. And also you could ask me, how do you figure out this morphism to try to produce this sequence? That's another point, right? Okay, but the idea is the following. Why such a morphism could do the job? The main idea is shape symmetry. And just to give you the idea before giving you the details is the following one. Just as before, I have some fixed point of the morphism. Believe me, there is one in that case. And the idea of shape symmetry is the following one. If you look at the image of, let's say, what occurs in position ij, and if you have some rectangle of some given shape, then what you will get in position ji, if you look at the image, what you should have is the transpose of what you had before. So if you have a permutation of your indices, then you will have a permutation in the shape of the image. That's the idea. And also to have things that fit together, if you take all the letters on the same line, they should have images with the same number of rows. And if you take all the images on the same column, they should have all images with the same number of columns. So you have some pretty condition to be able to put things together. That's the idea of the shape symmetry. But in 2D, it's pretty easy. You just have this kind of symmetry along the main diagonal, right? That's the idea behind that. And so it's not so nice to, after 1 hour and 50 minutes, to give formal definition, but the idea is just how can you glue together multidimensional picture. The idea is just the following. If you have one picture and another one, and if they have the same dimension here, then you can glue them together. That's just the idea of this slide. But there it's written in d dimension, and so just the idea is to say, okay, if you remove the ith coordinate, and if you have the same shape in all the other coordinates, so imagine that you have two kind of cubes, and if 2 of the 3 dimensions are the same, then you can glue them together because they have the same basis. That's the idea in 3D, or here in 2D it's even simpler. So this is when you can concatenate blocks together, and you define which dimension you will concatenate them together. So this is why there's this extra exponent I to tell you where you glue them together. And here, for instance, x and y, it's a 2 by 2 and a 2 by 3, so I can glue them just like this, but not in the other direction. That's pretty obvious. And if you have a map from an alphabet to some bounded picture like that, so you have rectangles of various dimensions, it's not always the case that you will get some morphism. I would like to have a morphism to be able to iterate the process and do the same again and again to have bigger and bigger blocks and apply the morphism iteratively. And so, for instance, on that example, gamma, you have these 4 images, and you can do some gluing in some nice way. For instance, you see A and C, they have the same number of columns. So if A is just above C, so I can glue them together here. A and B, if you look at the image of A and B, you have the same number of rows, so you can glue them here. That's still very nice. And D also is doing the job pretty well because it's a 1 by 1 block, so I can glue it here and glue it there. But then if you want to iterate, you are stuck. It doesn't work anymore because you will have problem with those dimensions. So this map will not give me a morphism. And so to have a d-dimensional morphism, I will say that for all letters in the alphabet, gamma n of any letters should be well defined from gamma n minus 1. And so you will have this condition that should extend for all possible n. Okay, And so what I wrote down here is exactly what I said before. The images of any two symbols on the same row must have the same number of rows in the images and the same for the column. Okay, and the definition of shape symmetry in general. So I give you now a morphism, which is now well defined. It produces some infinite word, and I will say that the fixed point of this morphism is shape symmetric with respect to the morphism gamma. This is exactly what I showed you in the ID before. If you take what's going on in some given position, x of n1 and d in d dimension, you apply gamma and you look at the shape you get, so you get some block of that shape. If you permute the component, so you look at some other point up to a permutation, the corresponding shape when you apply the morphism gamma should have a shape that is the same permutation of the dimension of the block you had before. So this is written in a complicated way, what I show you just here. The image of this block and that block, this one is just a transpose of that one. Here I just have these two permutations, so that's pretty easy in dimension 2. And so, just to convince you, with my big ugly morphism, I start with A, I iterate 1, my map, over 13 letters. I iterate a second time, a third time, and you see, I get something of size 2, 3, 5. You have the slides with you, but you guess what is the next one? 1, 2, 3, 4. Well, 1, 2, 3, 5, and the next one will be 8, because it works exactly like the Fibonacci sequence. And I keep iterating this, and I get this kind of picture. So I just put colors, but you see on this picture, you will recognize here where the P positions are lying, and the same for the symmetric part over here. So it seems to work pretty well. But then you will see, how the hell did you get all these 13 letters and this strange morphism? How is that possible? Actually, it's not so difficult. What I did, I take the picture and I cut it, not randomly. I decide to cut it with block of length 2 or 1. But do you recognize this sequence? Yeah, this is exactly the Fibonacci sequence. So I decide to cut my infinite 2 by 2 two-dimensional array with blocks corresponding to the Fibonacci sequence. And so I get some finite number of blocks. And from that, I can try some morphism. I have an idea that if I start with the A, I should have some block that behave like this. And so I know that the letter there will correspond to a block like this one. And so I try something. And I get 13 letters. And so, how do you prove this result? Actually, this is exactly the same kind of proof that all the proof I did before. On one hand, you have morphism and you want to iterate morphism. On the other hand, and it's exactly equivalent, you have some automaton and you are feeding the automaton with entries. And the two models give the same result. And so here, I know the morphism. And what I would like is to find the corresponding automaton. But from the morphism to the automaton, we can do the job. I know how to do it in 1D or in 2D. In 2D, it's the same. If the image of some letter is a 2 by 2 block like this one, I will say that I will have 4 edges. From R, from state R, I will go to S, T, U, V, and I will encode those 4 positions by the pairs which are here. Okay? And so it's the same job as before. I look at the automaton. Okay, it's a bit ugly, but you got 13 states, right? Why do I have 13 states? Because this is exactly the morphism which I propose here. I have these 13 states. So from this, you can build the automaton. Okay? Sometime, like D, if you look at D, there will be a single edge. Let's see, where is D? Where is D? That's a good, I don't even, I see, yeah, it's here. I have a single edge here. So if I have this automaton, you are tired, and the proof is almost over. What should I prove? That's a good question. I want to prove that the morphism is producing a bidimensional picture where the 1 corresponds to the p position, right? And during half an hour, what did I do? I show you that the p position were given with all this machinery, and my conclusion was what? That I know exactly p position. I write x and y in the Fibonacci system, and what is the condition? X should end with an even number of 0, and y is exactly the same, but shifted by 1, right? So, if you look at the language accepted there, what should be the language? I should accept Fibonacci expansions on the both component, and I should, so the outgoing arrow correspond to position where I will have a 1, right? And if you look, just to convince you, let's take a path like this one. I don't know, I will write it down so you will be convinced. Let's say I start from the initial state, and I do this, maybe a few times, and then this twice, okay? And so what do I get? I first get 1, 0, then 0, 1, 1, 0, 0, 1. Am I right? 0, 1, 1, 0. I'm not sure what I'm doing. 1, 0, 0, 1, 1, 0, and then 0, 1, and then twice 0, 0. 0, 1, and then twice 0, 0. And what are these two words? I should have taken the other part, but anyway, that's the same, because it's symmetric. It's exactly either one pile is smaller than the other one, so this is why you have more or less the two copies are the same, more or less. You just have to switch the two components. But what do you see here? Here, you see one component that ends with an even number of 0. That's fine for me. And what do you see there? You see exactly the same, but shifted by 1. So this means that I have recognized a p position. So if you take time after lunch and you analyze carefully this automaton, you will see that it accepts exactly pairs of words that are Fibonacci expansion, where one is the shifted of the other one by 1, and you get a final state exactly when one of the two components, the good one, has an even number of 0. And so putting everything together, I know that the morphism is doing the job I want. And it's a good time to stop here.
So, in your explanations of the definitions of higher dimensional substitutions,
yeah.
And this is, can it be algorithmic? You have an algorithm to check that this.
That's a very good question, because this is what I could say a few slides later. Maybe it's exactly your question. I mean, if you give me a map and you would like to know, is this map a d-dimensional morphism? That's your question?
Yes.
And this problem is decidable. So you have an algorithm, you give me the map, and it outputs yes or no. It can be extended to a morphism or not. So you can do it, yes, yes.
Slightly nicer.
Yeah. And in the same way, you can also decide if you give me now a morphism, you check it with the first algorithm, you give me a morphism that is producing some fixed point, and you ask me, does this fixed point, so is this image, does it has shape symmetry or not? And then you have another algorithm to tell me yes or not. So all this work was done by Arnaud Mas in his thesis and some of the papers. So if you are interested in this, I have Arnaud Mas' thesis in my office, so just ask me. If not everything is in his paper, so feel free to ask me. Yeah?
From what I've seen, all such morphisms, the image of a letter is a rectangle or in general a parallelepiped. Can you generalize to something which is not a rectangle? Like something like this?
Yeah, that's a good question. Yeah, I mean, I know that you can produce a kind of substitution like this way. Up to some extent, you can imagine that if one letter gives a block like this, maybe the symmetrical could give a block like that. So, but then I'm not sure that will fit in the right way. So I don't know about the answer, but it's maybe more tricky than just playing with rectangle, of course. And about decidability, I don't know.
Because we tried to build.
Yeah. I guess it's much more tricky, yeah. I have no idea.
Maybe you can attend the talk of Natalie. I think there is something like this. But okay, is there other question? Okay, maybe I have a last one. Is it the connection between Wythoff and Fibonacci world? Is it a coincidence, or for example, if I give you any morphic word, can you modify the rule of the game to get this morphic word at the losing position, the set of losing position?
I have several answers. I mean, when Eric Duchesne was a postdoc with me in Liège, let's say 10 years ago, this is what we tried to do at the beginning. So one of the first papers we wrote together was the Fibonacci game. So you give me the Fibonacci word, so I can define a game over 3 piles of token, but that game was not so nice at that time. I mean, the rules are quite complicated in the sense that they are not invariant. That's what I will talk about in my last lecture, but I have some strange rule. I don't remember by heart the rule, but like, if the 2 biggest pile are like this, then you can do that on the last one and not on the first one. But anyway, you can find a set of rules that is working. So this was especially for Fibonacci. Then we extend that to piso-cubic substitution. We have a general rule for that. So this means that I will have a word over a 3-letter alphabet, and I look at the position of the nth letter A, nth letter B, and nth letter C, and it will encode exactly the nth P position of the game. And then we work also in the direction of the Betti sequences. So if you give me a Betti sequence, there are a game associated with that.
Yes,
so
I mean, surely you must have restriction, otherwise it's easy to define the game and just, if you are on a Fibonacci world, go to straight to 1-0 and then you lose.
No, I want some kind of, I mean, you need a finite description of the rules, in some sense. That's the idea.
Okay, see if there is no other question, we go directly to the lunch.